So first of all, I would like to thank the organizers for giving me the opportunity to speak. And I think I will quickly move on to the presentation. So first of all, what is the motivation for my work? Basically, is an observation that in spectroscopic measurements in the light atoms, if we take a look at, for an example, first transition energy between the ground and first excited states, without including fine structure and so on. And we take a look at the experimental uncertainties, we see that the uncertainties are quite small. I will tell with respect to what they are quite small, but they're on the order of 0.1 centimeter to the minus 1 or less. And if we take a look at the state of the art in the theory for atoms, the situation is obviously quite different, because with growing size of the system, the accuracy deteriorates quite quickly. So as we can see, I'm showing here only the non-relativistic energy, so Schrödinger equation basically. As we can see, for the lithium, beryllium, borium, and very recently for the carbon atom, the situation is great. The theoretical accuracy can basically compete with the most accurate experimental measurements. But beyond that, we can see that the accuracy is much worse and the uncertainties are not so clear. And the most accurate at the moment calculations that I found come from either F12 methods or quantum Monte Carlo. Basically, maybe first thing first, so about the Hylleraas method. It's not a new method, it's quite classical method. It's a variational method. We solve the problem in the basis set. It is used in precise computations of few electron atoms and other this type of few particle systems. And it provides some of the most accurate results in the quantum mechanics. As I said, it's 90 plus years old, but in the original, in 1922 study, it gave 10 to the minus 4 accuracy, which was at the time comparable with most precise experiments. So how does it look in practice? Here we have, we can take a look at the convergence of the Hylleraas method and other methods for the helium atom. With the disclaimer that CI is a rough approximation of the convergence, it's not from the actual study because it depends on how you count number of the basis functions. But as we can see here, the Hylleraas CI, so the method that combines the traditional orbital-based approaches with Hylleraas method, is here. Here, the red one are explicitly correlated Gaussians, and here are explicitly correlated Gaussians with linear cusp factor. And here at the bottom, we have Hylleraas method. As you can see, the convergence is very fast. Of course, there are more precise methods, but they are very difficult to extend to larger systems, so they're of no interest, at least to me. Basically, if we use Hylleraas method, we introduce distance between the electrons directly into the trial functions. So we get great convergence, but at the great price. The integrals no longer separate because we have correlation factor that is basically functions of both electrons' position. For helium, it's of course not a big problem since the Coulomb operator connects the integrals anyway, but in the general case, if we include R12 factors, we get 3 n-dimensional integrals. And that is a problem. Using orbital approximation, we get 2 electron integrals in the worst case, which is 6-dimensional integrals, but we learn to deal with them. But when n is larger than 6, so the integral is larger than 6-dimensional, it becomes more and more complicated, obviously. So what is done for the three-electron atom. Here we can see trial function for the Hylleraas kind of trial function for the lithium atoms. So as we can see, it contains all the inter-electron distances and the distances of the electron from the, there should be R2 in here, I see in this R, and the exponential factor. So it leads to 9-dimensional integrals, which look more or less like that. And somewhat surprisingly, Fromm and Hill, some years ago, solved this type of integral, which is kind of a generalization because it has these factors in the exponential functions. And they found analytic expression for this kind of integral. So if you want to solve the Hylleraas function that I've shown you, we can use this Fromm-Hill integral, differentiated over Wi and Ui parameters as many times as we need, and take the Ui limits to the 0. And then there happens to be problem with evaluation of Fromm-Hill integral. And the problem is that the expressions for analytical expressions start to be very, very large for higher powers of Ri and Rij's. And they're difficult to calculate, even to keep in memory in some instances. So what was done some years ago, an alternative scheme based on recurrence relations was developed by Mariusz Puchalski and Krzysztof Pachucki to solve this problem. And I have to say it works exquisitely good. So here we have similar graph as previously, but for the lithium atom, where, maybe I didn't set that on the previous plot, but on the y-axis we have basically convergence with the exact or the best estimation of exact non-relativistic energy, and on the x-axis we have number of the basis statically. So as we can see, in this case, the CI method is more or less, there's star here because it's approximated. The Hylleraas CI immediately shows great convergence compared to the regular orbital-based methods. The explicitly correlated Gaussians are converging pretty quickly. And finally, Hylleraas shows very, very fast convergence, and it can be converged to the values that are enough for all practical purposes in terms of non-relativistic energy. So about the extensions to the 4-electron systems. Extensions of this technique can be applied, but within certain restrictions. Integral that would be actually 12-dimensional. In the general case, the solution is not known to be, is not known. So we have to impose certain restrictions in order to be able to calculate these integrals. So if we restrict the trial functions, the basis functions, to singly linked type, namely if we take at most one Rij factor in each term of the basis linear combination, we arrive at the basis that looks more or less like this.
Tymon, at least at most one Rij with odd power.
1 second. This is why I wrote here unlinked basis set. And what I would call singly linked is Hylleraas function that actually has additional even Rj factors. So this is I will show the results in a second, and yes, it will show that this unlinked approach, when we have only one power of Rij, is obviously not that good. So quickly about the integrals, if we restrict ourselves to this case, we arrive at integrals where we have at most 3 odd powers of Rij, so these correlation factors. And actually there are two kinds of these integrals. First, that I call star type integrals, because we have two second electron is connected in each with each other. The electrons are connected with each other through the second electron, as in here. So it kind of let's say looks like a star. And here we have chain type integral that connects linearly each electron to another. And basically, those types of integrals can be similarly, like in three-electron case, described and found using with analytic formulas. First one needs two kinds of master integrals, this J4 and I4, where all the powers are to the -1, where all r powers to the -1, and then we use the expressions that result from them. We use the fact that if we integrate over this A, B, C, and W nonlinear parameters, we can obtain other analytic formulas for higher powers of AB and for higher powers of R. Then if we want to restrict ourselves to the Hylleraas case, we need to take limit with respect to W's. And that's the way we can obtain integrals. So here we have convergence of various methods in the case of beryllium atom. Here we have the first one is the Hylleraas CI method. The second one is doubly linked Hylleraas CI. And the third one is explicitly correlated Gaussian, with the disclaimer that this last point is from the most recent study. So it's not part of this series, but as we can see here, the number of basis function is quite large on this plot. So let's focus on the small part of it. And here we can see more methods, because here I added this unlinked Hylleraas kind of functions that, as we can see, converge quite poorly. And also I added the single linked Hylleraas function, but with the disclaimer that in the case of double linked Hylleraas CI, the nonlinear parameters were kept the same in the pairs. And here we have explicitly correlated Gaussian functions. So
Tymon, you should sum up. Because
yes, I'm coming to conclusions. Okay. So in the beryllium, as we can see, the application of the method is possibly under some restrictions. If this gives decent but not yet great results, I'm working on that. The good part is that the error bounds can be clearly established, contrarily to F12 quantum Monte Carlo methods. Accurate wave function is also available, contrarily to the basis set extrapolation methods. And finally, there is a small number of nonlinear parameters to optimize, contrarily to explicitly correlated Gaussians when there are very, very many. So I think that's all I wanted to say. There are some perspectives for the future of extensions of this work, and beyond four-electrons also. And there are some people that I would like to thank. Maybe I will not take time. And thank you for, and another thank you for funding of the project. So thank you for listening.
Thank you very much for your talk, interesting. We had a question from Philip. Why are the errors difficult to estimate in QMC?
Because there are two kinds of errors. I mean, one, because, for example, in here we have nice convergence, so we can interpolate this function, but actually from what I've seen in the quantum Monte Carlo, there are two kinds of errors. First kind is stochastic, and the other kind is with respect to completeness of the basis sets. And from what I've seen in some works, when there are error bounds given for the quantum Monte Carlo methods, it later turned out that the error bound was much smaller than what turned out to be the difference between the lowest variational results from other methods and the result given by quantum Monte Carlo. So
there is no basis in quantum Monte Carlo. What you mean is that there could be an error due to the nodes in the wave function.
yes, due to the form of wave function. Yes, yes, exactly.
Okay, fine, thanks. There is a comment by Belen Ruiz.
Hello, here is Maria Belén Ruiz from the method Hylleraas CI. I have a comment, and this is when you have one inter-electronic coordinate per configuration to any power, this is equivalent to the Hylleraas CI, because higher powers one can express as a product of as a excitation, speed, the orbitals, and so on.
Yes,
the
yes,
difference
surely.
Is that you have done a different way of integration using the From and Hill formula. This is an alternative integration, but I mean that with a single inter-electronic coordinate, this is the method that came from James and Kilich and later Sims and Hamstrom, and this is in principle the Hylleraas CI method. This is
okay, thank you for the comment. I will look into that connection.
Mm-hmm. Okay, I don't see any other comments. Maybe I have a small question by curiosity. Yes. You said that you can generate all the integrals either by derivation of the W's and that was becoming difficult when you start derivating several times.
Yes.
Then the other solution is the recursion relation. I would like to know, is it stable also for large powers? I mean, if you do it several times, is the recursion relation stable?
I mean, the recursion
Let me answer the question. It's very stable.
Yes,
These recursion relations are very stable numerically.
There are some difficulties for very large differences between the nonlinear parameters, but in principle, it's very stable.
Okay, thank you very much. I don't see any more comments or questions, and therefore I would like to thank the three speakers again.